Section 2.2 again. Today, I want to show you more examples about the limit of a function. Before I present the examples, let's take a review about what we learned in the last class. Review number 1. Consider a function. In this function, x is independent variable. X can freely assume values. The variable y is called a dependent variable. The value of y depends on the value of x through this equation. Now, if as x is getting closer and closer to some point A, y is closer and closer to some other number L, then the number L is called the limit of the dependent variable y as x approaches A. Because y is equal to f of x, we also say that L is the limit of the function f of x as x approaches A. In notation, we write L is the limit of y as x approaches A, or L is the limit of the function f as x approaches A. Review number 2. Conventions about this limit definition. Convention 1. As x is getting closer and closer to the point A, in this process, x is not allowed to take the point A directly. For the dependent variable y, however, y approaches L, y can take the number L in this process. Review convention number 2. If Sx approaches A, y approaches more than one number. In the case, we say that y has low limit as x approaches A. In other words, we require the limit of dependent variable y is one and only one, is unique. Now, examples. Example 1. Find the value of this limit. In this limit, x is approaching 0 from the right-hand side. Now we need to determine as x approaches 0 from the right, what number this function will approach. The graph of this function is here. The graph oscillates between 1 and -1 infinitely often near the y-axis. As x is closer and closer to 0, the curve oscillates more and more frequently. This function is not defined at the point 0. When you plug in 0 in x, 1/0 is not computable. So this function has no function value at the point 0. From the graph, we can see that as x approaches 0, the curve approaches all the points between -1 and 1. When a function approaches more than one point, more than one number, we say that the function has no limit. Therefore, this limit doesn't exist. We can also use tables to tell the limit doesn't exist. Here I have made 2 tables. In this table, I let x approaches 0 by taking on these points. Function values at these points all are zeros. For example, when x is 1/2 pi, then 1/x is 2 pi, and sine of 2 pi is 0 by calculator. So when x approaches 0 by taking on these points, function approaches 0. Now in the second table, I let x approaches 0 by taking on these points. Now function value at these points all are 1. All are 1. For example, when x is 1 over 2.5 times pi, 1 over x is 2.5 times pi. And sine of 2.5 times pi is 1 by calculator. So therefore, as x approaches 0 by taking on these points, function approaches 1. So when x approaches 0, function at least approaches 2 different numbers. Therefore, we conclude that this limit doesn't exist. Example 2. The graph of function g is given below. The blue curve is the graph of the function. Now, based on the graph, answer these questions. The first question is a left-hand side limit at the point -1. As x approaches -1 from the left-hand side, what number the function will approach? -1 is here. Now, I let x approach -1 from the left-hand side. Then the curve approaches this point. The height of this point is 2. Therefore, this limit is 2. Now, the second limit. Second limit is the right-hand side limit at the point -1. X approaches -1 from the right side. We need to determine what number the function g will approach. -1 is here. Now x approaches it from the right side. Then the curve approaches this open dot. The height of this open dot is 1. Therefore, this limit is 1. Just like the previous examples, we can use tables to find these 2 limits. Here, I have made 2 tables. In this table, I let x approach -1 from the left side by taking on these points. Now, to find function values at these points, I need to go back to the graph of the function. When x is -2, here, x is -2 here. Then function value at -2, or the value of the dependent variable y at -2 is the height of the graph at -2. Yeah, is this height. This height is function value at -2. From this point to this point, the height, the distance is 1. So I guess this height is 1. So when x is -2, function value is 1. Now, when x is -1.5, 1.5 is here. Function value at -1.5 is the height of the graph at this point. That is this height, Now, from this point to this point is 2. So I guess this height is about 1.7. So function value is 1.7. Similarly, when x is -1.1, -1.1 is about here. Now, draw a vertical line. Okay, now from negative 1.1 vertical line, then to the curve. Yeah, this height, I guess, is about 1.9. 1.9. Similarly, to tell the function values at the other points, when x is negative 1.01, I guess the function value is 1.95. When x is negative 1.001, function value is 1.99. Negative 1.0001, function value is 1.999. So when x approaches negative 1 by taking on these points, function value is approaching 2. So the conclusion is when x approaches negative 1 from the left, function approaches 2. 2 is the height of this solid point. The second table is about this limit. X approaches negative 1 from the right side. And then x approaches negative 1 from the right side by taking on these points. Now, let me go back to the graph to determine the function values at these points. When x is 0, let me see. X is 0 is here. Function value at this point is the height of the graph at this point. The height of the graph at 0 is this height. Function value, the y value. This height, my guess, is about 1.9. Now, when x is negative 0.5 negative, about here, 0.5 negative, then function value at negative 0.5 is this height. My guess about this height is 1.5. Similarly, when x is negative 0.9, function value is about 1.2. X is negative 0.95, function value is about 1.1, and so on. Now, from this table, when x approaches negative 1 from the right side, by taking on these points, function approaches 1. So my conclusion is x approaches negative 1 from the right side, function approaches 1. The limit is 1. 1 this time is the height of this open dot. The third limit is a both hand side limit. X approaches negative 1. X can approach negative 1 from the left side, from the right side, or even by jumping around negative 1. From these previous two limits, we have seen that when we let x approach negative 1 from the left side, the function approaches 2. This point, the height is 2. When x approaches negative 1 from the right side, the function approaches 1. The height of this point is 1. So when x approaches 1, the function approaches 2 different numbers. Therefore, this both-sided limit doesn't exist. DNE doesn't exist. This limit doesn't exist. The fourth limit is a left-hand side limit at point 0. When x approaches 0 from the left side, the graph approaches this point. The height of this point, I guess, is about 1.9. So therefore, this limit is 1.9. This is a typo, not 1.5, not 1.5, should be 1.9. Now, this limit, the next limit is a right-hand limit at a point 0. X approaches 0 from the right side. X approaches 0 from the right side. The graph of the function approaches this point, the same point. This point, the height is about 1.9. So this limit is 1.9. Again, a typo, should be 1.9 here. This limit, the next limit is above side limit. X approaches 0. X approaches 0 from the graph. X approaches 0. X approaches 0. No matter how X approaches 0, the graph always approaches this point, 1.9. So the both side limit is 1.9. 1.9. Now, this limit, X approaches 1 from the left side. What number the function will approach? 1 here. X approaches 1 from the left side. The graph of the function approaches this open point, open dot. This open dot, the height is 2. So the limit, this limit is 2. This limit is 2. X approaches 1 from the right side. What number the function will approach? Approaches 1 from the right side. From the right side. The graph approaches the same open dot, open point. This point, the height is 2. So this limit is 2. Now, this limit, both side limit and 1, okay? When X approaches 1, okay, what number the function will approach? X approaches 1. X approaches 1. No matter how X approaches 1, the graph always approaches this open dot. The height of this open dot is 2. So both side limit is 2. The final two questions. What is the function value at -1? What is the function value at 1? At -1, the graph has a solid point here. Solid point is part of the graph. So at -1, function value is the height of this solid point. It is 2. So function value at -1 is 2. At +1, also the graph has a solid point here. Solid point is part of the graph. Open point is not part of the graph. So when X is 1, the function value is the height of this solid point. It is 1. Function value at 1 is 1. Here is a remark about this example. From this example, we can see that a solid point is a function value and an open point is a limit. Go back to the graph of the function. Solid point here. Its height is function value at 1. Solid point. Its height is function value at -1. Open point. Its height is the limit of the function when X approaches 1. Open point. Its height is the limit of the function as X approaches -1 from the right side. B. When the open point and the solid point at the same X value are different, the graph has a break there. This graph has two breaks. One is at -1, the other one is at 1. Solid point and open point, they are not at the same position, they're different. C. When the graph has a jump, the both sided limit there doesn't exist. Yeah, this case, the graph has a jump. At a jump, left-hand side limit, right-hand side limit must be different. Therefore, both sided limit doesn't exist. Example 3. Sketch the graph of this function. Then use the graph to determine the value of the point A at which the both sided limit doesn't exist. Because the function is defined piece by piece, we also sketch its graph piece by piece. The first piece, x less than -1. When x less than -1, the function is 1 plus x. The graph of 1 plus x is a line. The slope is 1. X cannot be equal to -1, so I put an open dot here to mean the point is not part of the graph. Second piece, when x is between -1 and 1, the function is x squared. The graph of x squared is a parabola. X can be -1, so I put a solid point here. X cannot be 1, so I put an open dot here. Now, the third piece. When x is greater than or equal to 1, the function is 2 minus x. 2 minus x, the graph is a line with slope -1. X can be 1, so I put a solid point here. This is the graph of this piecewise defined function. Now, use the graph to determine the value of the point A at which the both sided limit doesn't exist. From the graph of the function, we can see that at a point x is -1, the graph has a jump. When a graph has a jump, there both sided limit doesn't exist because left-hand side limit, right-hand side limit, they are different. When x approaches -1 from the left-hand side, the graph approaches this point. The height of this point is 0. Therefore, the left-hand sided limit is 0. When we let x approaches -1 from the right side, the graph approaches this point. The height of this point is 1, so the right-hand side limit at -1 is 1. Therefore, at -1, the both sided limit doesn't exist. Is there any other value for A? Both sided limit doesn't exist? I don't think so. Only at -1, both sided limit doesn't exist. For example, at +1, when x approaches 1, no matter how x approaches 1, the graph always approaches this point. So at +1, both sided limit exists. For this function, only at -1, both sided limit doesn't exist. So the conclusion is the value of A for which both sided limit doesn't exist is A is -1. Example 4. Find the value of this both sided limit. The function in this limit is psi of x over x. This is the graph of the function. At x is 0, the graph has an open dot because psi of 0 over 0 is not commutable. At 0, the function has no value. Now the question is, as independent variable x approaches 0, what number this function will approach? From the graph, as x approaches 0, the graph approaches this point. The height of this point is 1. Therefore, this limit is equal to 1. We can also use tables to find the limit. Here are two tables. In this table, I let x approaches 0 from the right by taking on these points. From the last column, you can see that as x is getting closer and closer to 0 from the right-hand side, the function value is approaching 1. Therefore, the limit is 1. From this table suggests the right-hand side limit is 1. In the second table, I let x approach 0 from the left-hand side by taking on these points. Again, the function approaches 1. The second table suggests the left-hand side limit is 1. Now, based on these two tables, we conclude that the both side limit is 1.